So here's one last thing that I started doing at the end of the semester last semester, which is putting together little compilations of stuff from the units. Normally I'd make one for the calculator work, just so you have something quick that you can reference, but for this section I only have like 3 calculator videos, and I'm not going to make a compilation of 3 things. That's more work for me than it'd be worth for you. So instead, I'm just going to give you this here, where I'm going to give a rundown of the main concepts for this unit. A lot of the formulas, the basic ideas. There aren't going to be any examples in here, but this is meant to be a quick reference that you can use just to refresh your mind on definitions, formulas, that sort of thing. Anyway, hope this helps, and happy studying. A bit exactingly, at least according to the book, the definition of statistics is that it is the science of collecting, organizing, analyzing, and interpreting data in order to make decisions. And when we're thinking about data, just to be clear, data is just that collection of information that we're trying to consider. So that's the information coming from whatever observations, counts, measurements, responses, the things that we're looking at when we're going to draw our statistics. That's our data. And again, when you think data, your head probably turns numerical. You start thinking about numbers like heights or weights or lengths, like with those books. But truth be told, data doesn't need to be confined into that kind of category. Things like qualities, like the fact that a book cover is red, is a data point. But it's just not the sort of thing that you measure in quite the same way as the length of a book, for that matter. And generally, when you're thinking about data, this is where phrases like studies show or according to research come into play. That's what we're doing with stats, is trying to use data to be able to make statements like that, whether they're useful statements or not so useful statements, where that distinction can be drawn pretty broadly based on context and what sort of evidence you have. So now we're going to look at how we can classify data sets based on the context in which we look at them. So population is the set of all possibilities, all outcomes, all things from which we are trying to draw some information. It's the set of everything. And when we're taking a measurement on a population, we call that a parameter. And in a lot of ways, we view a parameter as something that must be true, in a sense. It's sort of a universal value. And when we get further on in this semester, we'll see about how we can talk about how universal those values really are, and if they're actually as good as they're cracked up to be. But as good as a parameter can be, truth be told, it's usually a bit difficult to get a meaningful one. Like with the books, you can't necessarily go through every single one ever written to try and figure something out. There's just too many. So when we're talking about these sort of things, we usually restrict our scope a little bit, and we talk about things called samples instead. A sample is just a subset of the population that we focus on. Usually we like our sample to be representative, in a sense. That is, that when we take our sample, it meaningfully shows information about the population. It tells us something meaningful. It's not just noise because we happen to pick a weird group within the larger population. And when we look at samples, when we're taking measurements on samples, that's when we are drawing statistics. So in that way, we can think of statistics not just as the science of collecting and interpreting data, but we can think of statistics as the study of samples. And that's what we're going to be doing a lot of here, is looking at things that happen to samples and later seeing how those things that happen to samples compare to what we expect from populations. But it's important to bear in mind that when we're talking about these things just in terms of their definition in this way, there's a lot of wiggle room with regards to how we make the distinction between a parameter and a statistic, or between a population and a sample. Because really, the only difference between a population and a sample is whether or not we place what we're talking about in a broader context. The main thing you should be watching for is whether or not what you're trying to talk about, the group that you're trying to describe, is stated as being part of something bigger. That's where you get the idea of being a sample, as being something contained within a larger group. Next, we'll look at the branches of statistics, as it were, where here we make what I consider a bit of an unnecessary dichotomy between descriptive and inferential statistics. Even though I'm not a huge fan of this, I should still underline it to be sure. Where what we're looking at for descriptive statistics is essentially representations of data. It's where we're looking at collecting and describing what we find. Think things like graphs, tables, diagrams, just representations. Whereas for inferential statistics, we're looking at how we can draw those statistics in order to make conclusions and interpretations about the population as a whole that ideally the sample would be a representative of. Now, again, I do think of this as a bit of a false dichotomy, because realistically, if you're looking to draw a conclusion, you're going to want to be able to present your evidence in a meaningful way. And usually when people are presenting evidence, they're not just doing it in some pursuit of objective truth. They're usually trying to make a point. So yeah, we present these as separate, but it's kind of rare to have a study to draw statistics in such a way that you're really only looking for one or the other. Usually you want both. So now that we have a sense for what data is in the context of statistics, we're going to break down and categorize data a bit more exactingly in this section. So first, we're going to look at the difference between qualitative and quantitative data as two very broad categories, where qualitative data, because statisticians are very creative with naming convention, is qualities. It's descriptors that don't have inherent value to them. They don't have some inherent valuation associated to it. It just is. Like saying that this shirt has green on it, or this shirt is gray, or my hair is mostly brown, or my eyes are hazel. I don't know why I'm stuck on colors. But what we're looking at here are just broad labels that give descriptions but don't tell you anything about a value associated to those descriptions. Meanwhile, quantitative data is data that has both that sense of a label and also a value attached to it. These are things like measurements and counts. So things like height, that I am 6'1", or weight, that I weigh about 210 pounds, or temperature, that the human body is about 98.6 degrees, or that it's about 73 degrees in my apartment currently. Here, these are values, and these values have a weight to them, in a sense. Weight has a weight to it. Wow, it's very creative, isn't it? But the idea here is that you can make direct comparisons. You could say that 50 degrees Fahrenheit is less than 55 degrees Fahrenheit, whereas you can't compare, say, the color red to the color blue in terms of an objective valuation, although I'm sure some people would make arguments about that. But, well, those are more opinions, but the more I talk about this, the more I start to sound like Ben Shapiro in my head, not like that. Now we're going to finish this section with the levels of measurement, where we're going to look at them from least to most descriptive. That is, from having the most information given by the category to having the least information to the most information, excuse me. We'll start with the nominal level of measurement, which, like I said, statisticians are very creative. It means we're looking at names. That is, when we look at nominal data, we're just looking at labels. There's no value attached to that. There's no comparison attached to that. It's just a thing. We can think of nominal data as being purely qualitative. Next, we have ordinal data, where we are attaching labels, we are attaching names, but those names have an inherent order to them. To the next level, and we talk about interval data, where for interval data, we are going from names in order to names, order, and consistent ranges. But there's one thing that's missing with interval data that I'll talk about in a second. But really, the defining thing here is that there is a sense of consistency between the change within values in interval level measurements. And then if we want to take it one level further, we can go on to ratio. When we're looking at ratio data, we have names, we have order between the names, we have a range between the values, and we have a meaningful true zero. We also get ratios of values, but ratios of values are a bit harder to quantify. It's easier to think about things in terms of that true meaningful zero. That zero has a meaningful value. 0 inches indicates a complete lack of height. In the same way that if we go from a letter grade to a point system, a grade of 0 doesn't just indicate a bad grade. It indicates that you have earned no grade, that you haven't earned a single grade throughout whatever it is that you're looking at. It shows a lack. It doesn't just show a small amount, it specifically shows no amount. So fundamentally, there are two ways that we can collect data. We can either collect data through what are called observational studies or experimental studies. For observational studies, what we're looking to do is make our collections with minimal interaction, at least as minimal as possible. To an extent, there's always going to be an amount of it, and we'll talk about that later, but we want there to be as little effect from our observing the data as possible. On the other hand, for experimental studies, you are specifically going to be looking for the effect of something that you do, the effect of what's called a treatment, where we have the test or treatment group where you apply some action to them and you compare them to what's called the control group, the group on whom you do nothing. So you can see what the difference is between a group that goes about their everyday activities and a group that has specifically been treated for something. A couple other things to mention here before we move on are things called simulations and surveys. These are usually considered observational studies. They're specific kinds, where for simulations, what we're doing is trying to represent a situation that it might be difficult, impossible, or unethical to look at in real life with real people, as it were, or real things. On the other hand, for surveys, what we're looking at are getting responses from a population by directly asking them questions. When we're talking about this, it's important to bear in mind the potential effects of bias. And in this sense, when we're talking about bias, we're not necessarily saying that there's an influence in one direction or another specifically. We're just saying that there is an influence away from an answer that would be most accurate or correct to the situation. When we work with an experiment, we have a few goals to keep in mind. Mainly, we want to be able to have control, randomization, and replication. That is, we want what we get to actually have come from what we did. We don't want confounding factors, as it were, throwing off our results. From there, we want the selections we make for our study, for our experiment, to be fair and unbiased. And we want our results to be fair and unbiased, which is where the randomization comes into play. Because it's important to remember when we're talking about this stuff that, we may not be putting things in the fairest way. We may be coloring results. And one thing that can happen with an experiment is we can get caught by the placebo effect, which I'm sure many of you guys have heard of, where what happens is by being put in a situation where someone thinks they're being studied, even if they're in the control group, even if they're not actually having an effect to study, they might still get a reaction because they know they're being watched, because they know there's a chance that they've been given a treatment. So we want to be sure that this is as fair in that way as we can make it, that our results are as representative as we can get them to be. And one way that we can help that is by using blinding, in particular double blinding, where when we're talking about blinding, we're talking about making it so that researchers don't know who specifically is being studied, who is in the treatment group. And in a double-blind study, neither the subjects nor the researchers know who's being studied, which hopefully will give the best results. Best in the sense of most accurate rather than most ideal. Sometimes when you're looking for a particular treatment, you really want to get a result, but it is very important that even if you don't get the result you want, you know that that result is meaningful. Really bad things can happen if you get bad answers to important questions, even if they're the answers that going in you would have preferred to have gotten. So you have to be very careful with that. And then finally, you want repeatability. You want to be able to run the study and then run it again. You want to be able to have someone else take your exact design and try it a second time and see if they get the same results. Because unless you do test every single possible subject, there's always a chance that no matter how well you worked, something else in here could have gone wrong. So you want there to be the ability for someone else to try it again to see what happens, to see if it still works. And with all of this stuff, another way that we can help make everything work better is by looking at making the sample size larger. This is something that we'll talk about in more detail later on, specifically in Chapter 5, but generally when we're trying to look at a sample to represent a population, we can always make that sample better by taking more things into it. The bigger a sample gets, naturally, the closer it gets to a population. So, with our goal of minimizing error in mind, we have 5 main sampling techniques. The first is called random sampling, and the name kind of tells you what we're doing. If you're trying to identify what type of sampling is being used, usually you'll see the word random in there. For this, we want every possibility in the population to be equally likely, and then we have another specification on there where we say a sample is simple random if it is such that every sample of the same size is equally likely. This is something where often you'll be looking for a kind of random generation. Usually you see the word random, you know it's going to be random. Next, we have what is called a stratified sample, where I'll say that methods 2 and 3, when I get to 3, are fairly similar. The difference between the two is a little bit subtle, but what we do with a stratified sample is take our whole selection and break the population down into groups and select representatives from each of the groups. Then, for a cluster sample, we're going to start in much the same way. We're going to take our group and we are going to break it down into categories. And instead of selecting from each category, we are going to select things within. We are going to select entire categories. That is, what we are doing with a cluster sample is breaking into groups and then randomly selecting some of the groups in their entirety. So like I said, these two are very closely related. For stratified, we take representatives from each. For cluster, entire groups are the representatives. And then next, we have systematic sampling, where systematic sampling is, in my opinion, the easiest one to identify, where for this, what you do is make a selection based on a fixed repeated pattern, something like every 10th. Every kth is the general term that sometimes is used for this, where you are drawing based on a fixed repeated pattern. That is systematic sampling. And then finally, we have the worst, in many ways, sampling technique, which is convenient sampling. If you're ever wondering whether something drawn is a convenient sample, just think to yourself, did it seem lazy? Because for a convenient sample, you're drawing based on what is easiest. Convenient samples are just get what you can, don't worry about if it's any good, it's close, that's good enough. So check for laziness if you're thinking about whether something is a convenient sample. Frequency distribution is essentially just a table. But it's a table built in a specific way where what we're trying to do is take that numerical data set and categorize it. We're trying to build categories into those numbers that we can fit our data into, where we're going to look at the frequencies of the data, the number of times that the data falls into one of those categories, and we call those categories classes. And then thinking about the sort of construction we end up with, we get something where we're looking at those classes, those categories, in terms of ranges of numbers, where we have a sequence of lower class limits, the smallest numbers in the classes, and upper class limits, the bigger ends, where we have the class width, that's the size of the jump from one lower class limit to the next, that's the size of the jump that a class covers, and the range is the entire space that the classes cover, the largest minus the smallest. And this is something we'll see again later when we get all the way up to 2.4. But with this, with a construction like this, we have a much easier time being able to identify important or meaningful patterns in the data that some great big pile of numbers might not be able to tell us. Now we can look at this here and recognize that the two classes 6 to 10 and 16 to 20, whatever they may be, are the most common ones. That's where most of the data happens to fall in this case. And that's the sort of thing that might be a little bit harder to discern if all we had was every single data point in that set. And what we're going to see next is the process for how we can take a data set and turn it into something like that. For us, when we're talking about these things, again, our goal is to have a nice, concise way to show what's going on with the data set. And the two main ways that we look at it here are through things called histograms and frequency polygons. And I'll mention that the book in this section has a couple of others in here called relative frequency histograms and ogives, but those aren't as vital for us here, so I'm not going to talk quite as much about it. Anyway, for a frequency histogram, non-relative frequency, what we're doing is taking a bar graph, and we have the bars touching, where our horizontal axis is representing data values, in this case classes, where the vertical talks about frequencies. And in this way, to make the bars touch, we look at class boundaries as a way to close the gaps between them. So we kind of split the difference between those missing values on our class limits. But this isn't a universal constructions, by the way. And anyway, when we're talking about the frequency polygons, we're essentially doing the same sort of thing, except there we're taking our bar graph and we're adding a bit on the edges and making a line graph that runs through the middles of the tops of those bars to make sort of a polygonal shape out of them using the midpoints and frequencies. So with distributions out of the way, we're going to start talking about what are called our measures of central tendency in section 2.3, where when we're talking about central tendency, it's kind of a, I don't know, some might say pretentious, but that sounds a little bit derogatory. It's a bit specific of a way to talk about what's essentially an average. We're trying to figure out what happens to most of the data. If we're going to think about just taking some random representative out of the data set, about where should it be without much other consideration. And the place we're going to start talking about this is with the mean. And the mean is probably what most people think of when they initially think of an average. In particular, if you're looking on Excel, for example, when you compute the mean, you just tell it to compute the average. So it's very often thought of in specifically that way, where a lot of times people call it the arithmetic average. And for us, it's not going to be anything hopefully new. I mean, if you've probably seen computing the mean before, computing it as an average, it's just we have a little bit of extra notation here. So we're taking the same sort of idea to get the mean that you're probably used to. You look at all of the values in your data set, you add them all up, and you divide by the number of values in the set. Where when we're doing that in this case, we have this specific notation here that we work with, where we are taking the sum. That's what that sigma, the capital sigma of something means, take the sum of, and then we divide it by the number of things. Where, because we're talking both about populations and statistics, we have slightly different ways to talk about it. When we talk about a sample, the sample mean is denoted x with a little line over it, that's read x bar. Meanwhile, when we're talking about a population, we're looking at the population mean, we are talking about the Greek letter mu. And this hints at a pattern we're going to be seeing a lot more throughout the semester, but especially in our next section, that when we're looking at sample and population things, we usually denote the sample term, as it were, with an English letter that might have an accent, and the population term gets a Greek letter. Why that's convention, I'm not entirely sure, but it's how we generally do things. And in either case, the formula isn't actually different here. There will be some subtle differences in other formulas, but for now, the main thing is just that we're specifying the context in which we're computing the mean. One other thing we can do with the mean is look at what's called the weighted mean, where what we compute here is the mean in a situation where the values we have don't stand on their own, as it were. They have associated value intrinsic to them. And in that case, when we want to compute x bar, or mu for that matter, we take the sum of the products of the value times the weight over the sums of the weights. And actually, if we're going to compute the mean of a frequency distribution, it works in much the same way, where our weights are instead thought of as frequencies. Next, we're going to look at the median as a measure of central tendency, where what the median does is it just takes the data you have and finds the middle. This is one that requires very little math, as it were. So what you do is you take your data set and you put it in ascending order, or descending for that matter, but traditionally it's least to greatest, and you work your way down to the middle. If you're thinking about this in the elementary school way, you probably first saw it. You would go in and cross out the ends until you work your way down to that value that's stuck in the middle of the whole set, and that's the median. Where if you have an odd number of values, then the median is just that middle number. And then if you have an even number, so you got 2 stuck in the middle, the median is the mean of those 2 values in the middle. For our last measure of central tendency, we're going to look at the mode, where the mode is just the most common value in the data set. So if we're thinking about our height data one more time, we would look at this and see that both 44 and 46 occur twice, which is more often than anything else. So those would be the modes. And because we have 2 modes, we call that data set bimodal. If we have a single unique mode, we call it unimodal, and I'll talk about this a little bit more later, but here we're seeing one weakness of the mode, which is, well, it's not always guaranteed to be particularly useful. And if you have a data set consisting of entirely unique things, it's actually not of any value at all because it won't exist. But on the other hand, the mode works for data sets that you can't use other measures of central tendency for. The last thing we'll get to for this section is just a quick word on a few common patterns that occur within distributions, where the first one we'll look at is what's called the symmetric distribution, where we can think of the distribution as being symmetric vertically, I think is the word there, where if you draw a vertical line through the middle of the graph, you can think of the 2 halves as being reflections of each other, where the picture in particular here is a specific example of a symmetric distribution that's called a bell curve, and that's a really important curve that we'll talk about a lot more starting in chapter 5. But just important to know here, this is a pattern called symmetric. Next, we have the uniform distribution, where everything in there, all the classes, have roughly the same frequencies, where technically the uniform distribution is a symmetric distribution, but it's a special case, and when we're talking about the symmetric distribution, we're usually referring to something more of the Bell or normal variety than this. Then we have what are called the skewed distributions, where first we're going to look at this left skewed or negatively skewed distribution, where the tail elongates more to the left and the mean is to the left of the median. The term negatively skewed can be thought of as coming from the difference of the mean minus the median being a negative value because the mean is lower. On the other hand, we have positive or right skewed distribution, where the tail is to the right and accordingly the mean is dragged to the right away from the median. So thinking in terms of that positive definition, the mean is greater, so if you subtract the median from the mean, you would get a positive number. Where the first one we have is the range. And we already talked about the range. It's just the highest value minus the lowest value. It's not a very interesting computation, but it can tell us something quickly about the spread of our data. That, for example, looking at the batteries, the battery 1 has a highest value of 24 and a lowest of 4. so it has a range of 20 hours, while battery 2 has a highest value of 18 and a lowest of 10, which would give a range of 8 hours. Tells you that battery 1 is, in a sense, more consistent, exactly like we'd expect. Quick computation doesn't tell us a ton, but it gives us a bit more context, which is what we're looking for here. And we probably still want more. So then we'll build towards an idea called standard deviation. And this is really the most important thing in this entire section. But to understand what standard deviation is, we have to start with an idea called deviation, where a deviation is just a distance away from the mean. So it's some value x minus the mean, whether that's x bar or mu. It's just how far away something is. So if the mean is 4 and the value you're comparing it to is 8, you have a deviation of 4. Or if the value was 0 and the mean was still 4, you'd have a deviation of -4. It's just how far away the value is, either above or below from the middle. And that seems like the nice sort of thing to think about in the context of spread. So it makes sense to want to talk about something like an average deviation, and there is something called a mean deviation, but we very rarely look at it. Not entirely sure why though. Anyway, we instead look at what's called the standard deviation, which is its own sort of average deviation. It's just got a little bit uglier of a formula than what we normally got from averages, or at least what we got from averages in the last section, where to get the standard deviation, what you do actually changes a little bit whether you're talking about a sample or a population. For a sample, you take your deviations, square them, and add up the squared differences, then divide the squared differences by 1 minus the sample size, and take the square root of that whole mess. Meanwhile, for a population, you do the same sort of thing with sums of squared differences, but then you divide by the entire population size, not the population size minus 1, and then take the square root. Where for samples, we call it S, and for populations, we call it sigma. And there, at least to me, is a somewhat intuitive reason for why S has a different formula than sigma, and it's because when we're talking about a sample versus a population, we should always leave the door open for a little bit of extra variability, for the fact that we're not getting all of the information in the population, we're just taking some of it. And because we're just taking some of it, and this is specifically meant to measure variability, the sample should be a little bit bigger. So we make the denominator in the formula a little bit smaller, makes the whole thing a bit bigger. Long and short of it is, whenever you're looking at this kind of computation, you'll notice, or at least you'll begin to notice with practice, that S is always larger than sigma. And then from there, we can talk about variance, which is the square of standard deviation. And when you're going to compute this stuff by hand, you usually get the variance first. But an interesting thing happens with all of these squares and square roots, that the variance is kind of a unitless measurement. It's a measurement of square things, whereas the standard deviation specifically looks at things in terms of the unit that we're originally talking about. So really, when we're talking about running these kind of measures of variation, number one with a bullet is the standard deviation. One more quick thing we could talk about here that kind of ties the mean and standard deviation back together is an extra computation called the coefficient of variation, which I usually denote with the letters CV, which represents the ratio of the mean to the standard deviation. So CV is either sigma over mu times 100% or x bar divided by S times 100%, depending on whether you're looking at a population or a sample, respectively. What the empirical rule says is for a bell-shaped distribution, for a normal distribution, we have that about 68% of data is within 1 standard deviation of the mean, about 95% of data is within 2 standard deviations, and about 99% of data is within 3 standard deviations of the mean. And that says a lot, but really to understand this is better to look at a picture where we can see that on this graph of a distribution, we have these kind of windows around the middle. And in each of these windows, we're catching more and more of the data set. That in that one wide window, x bar minus x to x bar plus x, we've got about 34% in each side by symmetry. Then going out to x bar minus 2 to x bar plus 2, we're getting a couple more in the teens percentages, and then we get a few more going all the way out to 3 standard deviations away, where because that distribution gets closer and closer to the axis, we get less and less, but we are getting closer and closer to getting meaningfully all of the data. Although those ideas are things that we're going to have to wait until we get to chapter 5 to further develop. Meanwhile, for Chebyshev's theorem, we have that at least 1 minus 1 over k squared percent, the proportion of the data within k standard deviations of the mean. So, for example, if we were to make k equal to 2, we could say that 1 minus 1 over 2 squared percent, as it were, of the data is within 2 standard deviations of the mean, or 75%. That is at least 75% of the data is within 2 standard deviations of the mean. And Chebyshev's theorem is more general. It fits to most distributions, but the empirical rule is a little bit stronger, even though it's a bit more specific, because it gives a tighter approximation, in a sense. So for our last section of this chapter, of this unit, we're looking at measures of position, which thankfully is a bit less of an ambiguous name than some of the stuff we looked at in the other sections for this chapter. Basically what we're trying to do here is find ways to describe where a data point fits into the data set relative both to other points in the data set and special values in terms of the data set. And the first one we're going to look at here is quartiles. And this is the one we're going to spend probably the most time on this section, because there are a couple of other constructions we take with this. But we'll see later some other things with other fractals, and we'll see some connections to that here. But the idea with quartiles is kind of implied by the name quart, that what we're going to do is break our data set down into 4 parts using 3 grouping values that we think of as the first, second, and third quartile, which are generated based on medians. We're going to start by finding the second quartile, which is the median, but we call it Q2 in this context. And you can think of the second quartile as being something like the 50th percentile, because it being in the middle means that 50% of data is below it. And then from there, we get 2 other quartiles, Q1 and Q3, where Q1 is the median below the median. That is, it's the median of values between the minimum and Q2. So we can think of that as being like the 25th percentile, because 25% of data is below it. And then we get Q3, which is the median above, between the median itself and the maximum. We can think of that as being like the 75th percentile, because 75% of data is to the left of that. And with our 3 spacers, we've got 1, 2, 3, 4 groups that the data will fall into. Now we're going to look at a way that we can use quartiles to quantify unusual data in terms of a value called the interquartile range, or IQR, where the interquartile range is just a representation of where most of the data lies. It's the range of values between Q1 and Q3. It's that middle 50%. And for us, the most useful thing we have about the IQR is how we can talk about outliers in terms of it, where you think of an outlier in general as an unusually large or small value, a value that doesn't fit the rest of the data set. And here, we define that in terms of the IQR by saying it is a value that is 1.5 times the IQR away from the ends of it. So actually, let me just draw a quick picture here to help illustrate the idea. So let's say we have our data set, and it's something like before. So we're going to have our value for Q1 down there, and our value for Q3 is over here, and Q2 is somewhere in the middle. This range here is the interquartile range that we're talking about in this context. And what we do to find an outlier is we take 1.5 times this value. So we take this and go a little bit wider out. We subtract it from Q1 to go a little bit further over here, add it to Q3 to get a little bit further over there. So that if we get some value that's way out here, that's well outside that, that's more than 1.5 times the IQR above Q3 or somewhere over there, but I don't want to draw on my wall, we can say that it is an outlier based on its position relative to the data set. So now we're going to look at what are called box and whisker or box plots. And what a box plot does is it takes the information in terms of quartiles that we saw earlier and uses that to give a nice representation for the behavior of the entire data set, where it uses something called a 5-number summary. And the 5-number summary is just a quick way to talk about generally the shape of the data set. It takes the minimum, Q1, Q2, Q3, and the maximum as sort of a picture for what happens to the entire data set, and then we use that to construct a oddly shaped plot, where what we do is construct a horizontal scale that spans the data. So you draw an axis below, then you plot the 5 numbers above the horizontal scale. That is, you plot the values from the 5-number summary, then draw a box above the scale from Q1 to Q3 with a vertical line above Q2, and draw whiskers from the box to the minimum and maximum entries. Where I'll say that for this construction there are a couple of variations that we can use. For one, sometimes you'll see these things made vertically instead of horizontally, but it still has the same meaning. And another thing that can change here is sometimes when you're talking about a box plot, you don't want to include outliers because they don't actually have a reasonable meaning for the data set. So we'll throw those out and instead use the values on the edges of the range for an outlier in terms of the IQR as the representative instead. So before I move on to talk about z-scores, I do want to touch on one other kind of fractile that's somewhat important, percentiles, where here we're breaking our data set into 100 groups, breaking them off into percents to get a sense of where a data point is in relation to the others. So the last thing we're going to look at here is what are called z or standard scores, and the name standard hints at a thing called the standard normal distribution. And for those of you who have taken a stats course before, that's probably what you think of when you hear z-score. And I'll say that that's something we are going to see, but for now, we're just talking about it specifically in terms of data sets where we have a point, the mean and the standard deviation, and we want to compare that to a similar data point, but in a different distribution. Because it might be natural to look at your score on one class's exam and see how it stacks up to what you did on another exam, where if everyone did really terribly, like everybody got 40s and you got a 70, even though that's a not great grade, that might actually be a more impressive grade than getting an 80 on an exam where the average was a C. Because you weren't especially good compared to your peers, whereas that other score, despite being some might consider mediocre otherwise, was actually really good for how most people did. Because what we do when we compute a z-score is look at distance from the mean in terms of standard deviations. So we have some data point x, we subtract from it our mean, either mu or x bar, and then divide out our standard deviation, either sigma or s, that tells us how many standard deviations above or below the mean value the data point we're looking at is. And this gives us a great way to compare things that should be comparable but aren't directly, at least not fairly.